YouTube video. Today's YouTube video is dedicated to Josie, or no, Maddie. No, Marty. Raisa. Who knows? It's dedicated to all of you guys, okay? Great day. It's the fundamental theorem of algebra. And you say to yourself, well, Mr. Guest, we've been doing algebra for years. We must know the fundamental theorem of algebra already. Well, you know part of it, and you know this. Every polynomial of degree n has exactly n solutions, or zeros, or roots. Well, that's not the only thing that the fundamental theorem of algebra says. And by the way, it's super complicated to prove. You have to take courses in modern algebra and analysis and other things like that, number theory and in group theory, and you come up with a super complicated proof. But it's really interesting to see if you ever decide to go get a degree in mathematics. You get n solutions or zeros or roots. And what we learn then is that every polynomial, because it has those number of solutions, let's suppose that those are the solutions, that we have a solution of, say, 2 and 5 and 8 and 10. It can be written of this form, x minus each solution. So x minus c sub 1, x minus c sub 2, x minus c sub 3, dot, 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 x minus c sub n. What that tells us is that every polynomial can be factored. It's just difficult for us sometimes to see how it's factored. Now, what's the a out front? There might be a multiplier, a coefficient that you have to have sitting out front in order to make that statement true. That's it. There's one more part to the fundamental theorem of algebra. It doesn't seem like a big part, but it is crucial to making this work out. If a polynomial has a solution of a plus bi, then another solution must be a minus bi. What that tells us is that complex solutions, imaginary solutions, they come in pairs. You can never have just one. You would have to have two. If you see that there's three, there must be a fourth. They always come in pairs, and they match up as conjugates, which is really nice and useful. So let's get to work. We are going to analyze x to the fourth minus 16. We are going to list the number of complex roots. We're going to list the number of positive real, the number of negative real, the total real, the number of imaginary, and finally, the solutions. And then we will write it in factored form. This is the basis for your assignment today, and this would be a great example of a problem that you'll get on the test. And so I start right away. Easy question. How many complex solutions are there? 4. Complex means the total number of real and imaginary together. Okay? Do you remember from a previous lesson how we determine how many positive real solutions there are? What do I look for? The changes of signs. Yeah, the changes from positive to negative. Does this change sign? How many times? So therefore, I have one positive real solution. How do I determine the number of negative real solutions? P of negative x. So when I type in a negative x, negative x to the fourth is just x to the fourth, and then minus 16. So as I look at p of negative x, how many sign changes are there now? There's 1. So think about this, folks. There's one positive real, and there's one negative real. So how many total real solutions are there? There are 2. Any questions there? So if there are 2 that are real, and there's a total of 4, how many must be imaginary? 2. Let's find them. Does it factor? To what? X squared, minus 4 plus 4. Sweet. Does x squared minus 4 factor? X minus 2, x plus 2. We don't normally factor the sum of two squares, do we? But we could solve for that. We would say, where is x squared plus 4 equal to 0? And we would subtract the 4. We would square root both sides. X is equal to plus or minus 2i. So I go to list my solutions. And from right there, I have solutions of plus or minus 2. And from over here, I have solutions of plus or minus 2i. Agreed? Now, watch. How many total solutions did I find? How many positive real solutions did we have? 1. How many negative real did we have? How many imaginary did we have? And we had 2 total real. It's kind of cool, a diagnosis ahead of time, doesn't it? I mean, you don't have to love it. You don't have to like decide you're going to major in it. But you got to be able to appreciate that that's pretty cool, that it shows you how to do that from the very beginning. So the last thing we want to do is, it's going to seem like not that big of a deal, but trust me, in mathematics it is, and it's going to help us later on in our lesson. We're going to want to write it in factored form. And so when you write it in factored form, it's always x minus, x minus, x minus, x minus. And you just put the solutions in there. So x minus 2, and then x minus negative 2, so plus 2. X minus 2i, and x minus negative 2i, so plus 2i. That is the factored form of the polynomial. Every polynomial may be written in factored form. That's one of the parts of the fundamental theorem of algebra. So if you were to multiply that all out, what would you get? X to the 4th minus 16. Very good. We all good? Folks, if there's any part of the next problem we go through where you're like, Mr. Gantz, that's not clicking, stop me and ask me, okay? Complex solutions, positive real, negative real, total real, imaginary. We'll list our solutions. Again, solutions, roots, and zeros are all the same. Why don't I choose just one? Well, because the ACT, all sorts of different books and everything, they use different terminology, so you should be familiar with all of them. How many total complex solutions will I have? 3. It's the first part of the fundamental theorem of algebra. Look at the degree. That tells us. Positive real. None. Right? There's nothing there. No sign changes. Got it? Now I do p of negative x, and when I do a negative x cubed, I will produce a negative. So I have negative 8x cubed and then plus 1. How many sign changes there? 1. So if I have 0 positive real and 1 negative real, how many total real will I have? Great. I've got 1 real solution. There's a total of 3 that are complex solutions. So how many imaginary must there be? 2. Look at how we've diagnosed the problem even before we've started. Does that factor? Sam's nodding yes. You got an idea? No. He says it factors. Difference of squares? No. Common factor. Sum of, starts with a C, rhymes with oobs. Cubes. There you go. Sum of cubes. You all know that. You were just kidding me, right? Thank you. Thank you for humoring me. Makes coming back much more exciting. I'm trying to like pick through your brain. So, all right. So 8x cubed. What do you cube to get 8x cubed? 2x. What do you cube to get 1? 1. Do you remember how we finished this off? Square the front. Square the back. Multiply the two together. 2x times 1 is 2x. Do you remember the signs? Soap, same, opposite, always positive. So what's the solution here? Yeah, look at that, folks. 0 positive real, 1 negative real. There it is. This does not factor. If it doesn't factor, what do I use? So the Q rhymes with quadratic. Quadratic formula. Negative b plus or minus square root of b squared minus 4 times a times c. All over 2a. So I got 4 minus 16 is negative 12. How do I simplify the square root of negative 12? And I take out the perfect square root of negative 4. What's the square root of negative 4? 2i. So I've got 2 plus or minus 2i roots of 3 over 8. Can I simplify that? Yeah, I got 1 plus or minus I roots of 3 over 4. So we have our solutions. We have negative 1/2, and then we have 1 plus or minus I roots of 3 over 4. And this did exactly what we thought it was going to do. It found 3 total solutions. None of them were positive. 1 was a negative real. There's a total of 1 real solution. It's just negative 1/2. How many imaginary? There are 2 of them right there. Problem diagnosed. We write it in factored form. X minus negative 1/2, so plus 1/2. X minus the quantity, 1 plus I roots of 3 over 4. And x minus the quantity, 1 minus I roots of 3 over 4. Now I'm going to try to make my one last point here. If I multiplied this all out, what should I come up with? But I don't. I don't. What's x times x times x? I needed 8x cubed, right? The fundamental theorem of algebra says that it can be written in factored form, but you might have to put a coefficient out front to make it come out. See how I did that pretty easily? Good work. Thought we were going to lose the game. All right, complex solutions. Positive real. Negative real. Total real. Let's see after that. We're going imaginary. We're going to list our choices for this one, and we will list our solutions. Sweet. How many complex solutions are there? 3. Positive real, that will be the number of sign changes. How many sign changes are there? There are 3. So I do 3 or, yeah. Remember, when you do the positive and negative real, you have to decrease by a factor of 2. Okay? So I've got 3 or 1. I will look at the negative one. So I do p of negative x. And that produces negative 2x to the third minus 13x squared minus 26x minus 10. How many sign changes do we have there? None. There's none. So let's pair these up. If I have 3 positive and 0 negative, that would be a total of, or suppose I don't have 3 positive. Suppose I have 1 positive and 0 negative. That would make 1. Now, here's where it's different. Got to focus on this. We have a total of 3. If I have 3 complex and all of them are real, then how many imaginary would you have? None. Suppose you have 3 complex solutions, but only one of them is real. Then you would have 2. See how the total real decreases by a factor of 2 and the number of imaginary increases by a factor of 2. Excellent. Does that factor? Now we're totally out of luck, aren't we? Yeah, forget it. Like, we're done. We quit? Probably. All right. Thankfully, we got this thing called the rational roots theorem, though, right? Rational roots theorem says, hey, if it doesn't factor, just check your p's and your q's. What are the p's? 1, 2, 5, and 10. What are the q's? So I take all the p's, divide by all the q's. That'll be a plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. And then I got to divide them all by 2. So that'll be plus or minus 1/2. Plus or minus 1, we already have that. Plus or minus 5 halves. And plus or minus 5, but we already have that. So there's my solutions. So which one do you want to try? 1, doesn't work. Sorry. 2, doesn't work. 3, not even a choice. Should we try any negatives? Should we try any negatives? No, we know there's no no negative solutions. Now, I know the one that works, and it happens to be 1/2. But suppose you tried 5. I'll just roll through it once. Do you like to take 5 and cube it? So here's an easy way to roll through it. Just take 5 and run it through your synthetic division. If it works out, what should you come up with for an answer for a remainder? Yeah, so if you drop the 2, then we got 10, -3, -15, 11, 55, 45. So that didn't work, did it? So let's try something else. Do you like to plug 1/2 in? I don't. So just run it through synthetic division and see if it works out. It's a quicker way. You're less likely to make a mistake. 2, -13, 26, and -10. Let's run that through and see what happens. 2, 1. -12, -6. 20, 10, 0. Sweet. 1/2 worked. So for my solutions, I can list 1/2. 2x squared minus 12x plus 20. Does that factor? You take out a what? Take out a 2. You get x squared minus 6x plus 10. Does x squared minus 6x plus 10 factor? No, so what do I have to use? Quadratic formula. Fortunately, we're really good at it. Just think if we weren't very good at it, then it would be a really bad deal. But we're really good at it. Negative b plus or minus square root of b squared is 36 minus 4 times a times c. Looks like I got 36 minus 40. What's the square root of negative 4? 6 plus or minus 2i over 2. What is 6 or plus or minus 2i over 2? 3 plus or minus I. I'm going to verify my result. I'm supposed to have 3 solutions. I've got 3. I'm supposed to have either 3 real or 1 real. I've got 1 real. It's the 1/2. I'm supposed to have one that's positive. It is positive. I'm supposed to have 0 there, negative. I don't have any negative ones. I got a total of 1 real. I got a total of 2 imaginary. They're right here. So it should always verify. If it doesn't, you did something incorrectly. Last thing I'm going to do is write in factored form. X minus 1/2, X minus 3 plus I, and X minus 3 minus I. X times X times X gives me X to the third, but I don't want just X to the third. I want 2X to the third, so drop a 2 in front. What do you think? Not too bad? All right, should we try something easier? Let's go backward. I gave you the polynomial, and you found the solutions. How about now I give you the solutions, you find the polynomial? Sounds super complicated, but it's really not difficult at all. Write a third-degree polynomial with solutions of 4 and I. Well, here's where I start. I say, well, I got to write solutions with 4 and I, and it's third degree. So there should be a total of three solutions. I know one of them is 4. I know one of them's I. What would the third one be? Anybody know? Negative I. Because we know that imaginary solutions come in pairs. And it's always the conjugate. So that means that the polynomial will be of the form x minus 4 times x minus I times x minus negative I or plus I. Could you multiply that out? I wouldn't encourage you to start there. I'd encourage you to start here. X minus 4 times x, x squared, x times I. Just raise xi. Sounds like a Super Bowl or something, huh? Negative I times x is a negative xi. And then negative I times I is negative I squared. Now, I know that looks like garbage, but the fact is that all the i's should somehow disappear. Notice that the positive and negative xi's go away because they are conjugates, and I am left with an x minus 4 times x squared, and then what does the negative I squared come out to be? Positive 1. Hey, that's pretty cool. Now we could just multiply that out. X times x squared, x cubed. Negative 4 times x squared, negative 4x squared. X times 1 is x, and negative 4 times 1 is negative 4. Now, the fact is, you guys, that problem is a lot easier than the problems we just did, right? But people will get those problems wrong on a test all the time. So if you have questions about as you go through assignment, make sure that you come and see me. Let's go through it together. One more problem we could call quits for the day. Write an equation for a polynomial with these solutions. And this is going to be a third degree as well. If it's third degree, what's my third solution then? Negative 3 is 1. 4 minus 2i roots of 3 is another. So what's going to be the last one? 4 plus 2i roots of 3. It's just the conjugate. So that means I'm going to have x plus 3 times x minus parentheses 4 minus 2I roots of 3 times x minus 4 plus 2I roots of 3. Some of you take tests more quickly than others. Good for you. Must be nice to be so smart. When I work too quickly, I make mistakes here. Got to slow down. The past 2 hours, people got a little bit antsy during this time. Make sure you just follow what my first step is here. I'm going to get rid of this set of parentheses right here by distributing the subtraction sign. There are ways to do it without getting rid of that subtraction sign here, but when I've tried to teach you like in that past, everybody's gotten confused. So, although we celebrate confusion, we don't want to dwell there for too long. Is everybody okay with the first step? Okay. Then it's not a whole lot of fun, but trust me, it will work out. We're going to leave the x plus 3 by itself for a little bit here, and we're going to venture into that thing right there. I got to multiply all these out. I just start with the x's. X times x, x squared. X times negative 4, negative 4x. X times negative 2I roots of 3, negative 2xi roots of 3. And I know you write it, you're like, I've never written that before in my life. Yeah, I get it. It's odd, but just trust me. Okay, well, that wasn't too bad. We move on to the negative 4 now. Negative 4 times x is negative 4x. Negative 4 times negative 4 is positive 16. And negative 4 times negative 2I roots of 3 is positive 8I roots of 3. Pretty disgusting yet, right? Okay, let's hope something works out in this last set here. I move on to the 2I roots of 3. 2I roots of 3 times x is 2xi roots of 3. 2I roots of 3 times negative 4, negative 8I roots of 3. And 2I roots of 3 times negative 2I roots of 3 is negative 4I squared roots of 9. What do you notice? What cancels? That guy is gone with that guy. Sweet. I like that. 8I roots of 3, negative 8I roots of 3. Sweet. So I've got x plus 3. I've got the x squared. Now that's gone. I got a negative 4x, and a negative 4x makes negative 8x. Shoot. I got 16. I got negative 4I squared roots of 9. What is that negative 4I squared roots of 9? I squared will produce negative 1, so I'll turn that to a positive. And then the root of 9 is 3 times 4 is, that works out to be 12. Oh, thank you. Plus the 16. Seeing if you're awake, Jensen. Now the rest, that's algebra 1, right? Multiply it out. X cubed minus 8x squared plus 28x plus 3x squared minus 24x. 28 times 3, 84. Combine like terms. We have a minus 5x squared We have a plus 4x. We have a plus 84. That, my friends, is the polynomial. That's a little bit more complicated than the first one, wasn't it? Good work, you guys. Long lesson.